So here we've got an aluminum elbow that's bolted to a pipe. We know things like the mass of the aluminum itself is 2.4 kilograms. We know the mass of the water inside of the fitting is 3 kilograms. And we know the pressure of the water entering the elbow itself. The water is going to flow, it flows steadily through the elbow and exits as a free jet, meaning the pressure of the water here is atmospheric pressure. And there's some pressure, higher pressure at the inlet of the elbow that forces it through. Ultimately, we're going to want to find the force of the bolts holding the elbow in place. And to do that, we're going to be working with these two equations. For right now, let's ignore the right-hand side of these equations. Before we can even work with them correctly, we're going to need to identify and brainstorm some forces acting on the left-hand side. So from this perspective, we can observe directly where the bolts will be holding the elbow in place. We can also look at an area in which the fluid is entering the elbow itself. Remember, this is under a pressure of 30 kilopascal at that location. And we can also examine where the water is leaving the elbow. And the question we've got to answer are, which of the following things should we include in our sum of forces? Well, the first option is the force of the bolts on the elbow. And I say, well, yeah, definitely we'll want that because that's kind of the overall objective of the problem, is to figure out the force of the bolts on the elbow. So let's call these anchoring forces. So I'm going to call this FAX and FAY. I'm writing out the sum of forces in the x and in the y directions. So the next option is to include the force of the water on the elbow. If we look at a cutaway view of the elbow, it sure looks like that's a force acting on the control volume. You know, it sure is tempting to say, yeah, there's a force here, the water acting on the elbow in that direction, clearly because it goes around that corner. However, be real careful, because we're identifying the control volume as being the elbow itself and everything inside of the elbow. So in the highlighter here, I'll highlight the actual control volume itself. And this control volume includes the entire elbow. The force of the water on the elbow is an internal force, and you do not include that in your sum of forces. Another thing that we would not include is the force of the elbow on the water at that location, because that force is also internal. It's internal because we're defining the control volume to be the exterior of the elbow itself. So two forces that we would not include would be the force of the water on the elbow and the force of the elbow on the water. However, if we highlight the exterior of the control volume from this perspective, the question now becomes, is the weight of the elbow itself, is that an external force? I said, well, yeah, that is. That's gravity pulls down on the elbow itself. Gravity is external to our control volume. Gravity also acts on the water within the elbow, so within the control volume itself, and we also include that. So I'm going to write those in the y component. So we'll say the weight of the elbow is going to be the mass of the elbow multiplied by gravity minus the mass of the water inside of the elbow multiplied by gravity. And then finally, the question is, do we include the inlet pressure multiplied by the inlet cross-sectional area? And this is kind of subtle, and it's easy to miss because the fluid is flowing and it's hard to conceptualize what this pressure is doing. But if we look at the back side of the elbow, there really is a pressure acting on the control volume itself, and it's acting over this area right here. So the pressure at that location multiplied by the area of that circle. And from this perspective, the pressure is pushing the nozzle into the screen, and the bolts are helping to prevent the nozzle from flying into the screen. So we've got the force of the bolts pulling out at us and the force of the pressure pushing in away from us. So we do include that in our sum of forces. So the inlet pressure multiplied by the cross-sectional inlet area, note that that only acts in the x direction. So from this perspective, the pressure is acting uniformly over that circular area, and that acts to the right. So I'm going to include that in the sum of forces in the x direction. So I'll call this plus P1 multiplied by the area at location 1. And let's call that location 1. So now you might be looking at this. In the x direction, we've got the pressure, we've got the anchoring force on the bolts, and you might say, well, clearly there's flow of the water has to have something to do with this. And yeah, it does. It does, and that's what we're going to be accounting for on the right-hand side of this expression. So if you did do something like include the force of the water on the elbow, it turns out that you'll be double counting, and all of that is enclosed in the right-hand side of the equation. So it's an internal force, don't include it. And you might also be saying, well, yeah, there's also the force of the elbow acting downward on the water. Clearly the water enters horizontally and it leaves with a downward component. Well, yeah, that also is going to be included on the right-hand side of this equation in the y direction. So now we've gotten the left-hand side of the expressions correct, and we'll work on the right-hand side later.